Today we have lecture number 3, deriving momentum equation on the subject of fluid mechanics 2. In earlier we have already derived continuity equation, and before that we have discussed Newton law of viscosity and the definition of the fluid in lecture number 1. In this lecture we will start our discussion by Newton's second law of motion, which is actually the basis for deriving the Navier Stokes equation. So when we talk about forces, we will broadly classify forces in terms of body forces and the surface forces. And then we will apply the Newton's second law of motion to a differential element of a fluid, and we will derive momentum equation. And by using the Stokes postulate, we will be able to derive Navier Stokes equation. Okay, let's start with what is Newton's second law of motion. And Newton has defined in terms of momentum. So it is actually the mathematically we can say that the rate of change of momentum is equals to the net force that is acting onto the system. So momentum is a product of mass and velocity, and the net force acting on a body would be the rate of change of momentum. So how fast the momentum changes would be representing the net force that is actually acting onto the body. So here we see mathematically it is we have mass times velocity product, and we are taking its derivative with respect to time t. So if we apply the product rule, so we can say it would be v times dm by dt plus m times dv by dt. So for a special case, when your mass is constant, so the term here dm upon dt would be 0. So you whatever the velocity vector is, but if the mass is constant, then this term would be 0. So 0 multiplied by the velocity vector would turn into 0. So you end up with only this term, mass times rate of change of velocity. As we have already seen, the rate of change of velocity is actually acceleration. So you end up with F. So it is important to understand that this force F is not the applied force which has caused acceleration to an object having a mass m. So it is actually the net force. Just to get this mass m, your applied force is P, and obviously there are some resistive forces. It could be a drag, it could be a friction between the two contact surfaces. So here, if we are interested in accelerating this mass with an acceleration a, so this according to Newton's second law of motion, so the mass times acceleration would be equal to the net force. So the net force would be the applied force minus the resistive forces. So the net force is actually responsible for accelerating this object. It is not the applied force. So for example, in a case, let's say, if you are applying a force of 10 Newton, and let's say the contact friction is 10 Newton. So once you apply 10 Newton force, and here it is also 10 Newton or maybe 20 Newton, so your 10 Newton won't be able to accelerate this mass. So let's say if your force, applied force, is more than the resistive force, then the net force would make this object accelerate. So this is an important concept based on Newton's second law of motion. We can write acceleration using that Newton's second law of motion by bringing mass in the denominator. So force per unit mass would be the acceleration. So here F is the net force acting onto the mass, and A is its resulting acceleration. In fluid mechanics, since we are dealing with fluid, and fluid has an important property, density, so what I do is I multiply and divide by the volume. So as you know that mass per unit volume would be, this term would be a reciprocal of density. So we can say this term is a reciprocal of density and force per unit volume. So we can have an expression by which we multiply density by acceleration, we are going to get the force per unit volume. So density times acceleration would be the force per unit volume. So as we already know, acceleration we can write in terms of a material derivative, and acceleration has two components, local component and convective component. So this is actually the instantaneous part of the rate of change of velocity actually, and this is due to the change of position, how the velocity change is responsible for this acceleration. So we can write acceleration times density is a force per unit volume. So instead of acceleration, I just substituted dv by dt, material derivative, and we use because the force has a unit of Newton and the volume is in meter cube, so we define another quantity by small f, which is actually the force per unit volume. So F is the force per unit volume and its units would be Newton per meter cube. So instead of talking about force in fluid mechanics, we used to talk about force per unit volume, which is actually the rho times the acceleration. Now we talk about the forces. On a fluid element, there are two types of forces which are actually acting. So force which is actually a body force and a surface force. And so according to Newton's second law of motion, the forces that are actually acting would be either the body force or the surface force or both of them. So the rho times acceleration would be the force per unit volume, and this is either a body force or a surface force. We will define it. A body force is actually the force that has been acting on every particle of the body. So every particle is experiencing a force that would be called as a body force. Whereas the surface force is actually the on the surface, the force that has been acting onto the surface. So once you talk about a surface, obviously you have to define certain area over which the force is acting. So that surface force, as we know, the weight of an object is actually acting on all parts of the body. So here weight would be termed as body force. Whereas these normal or perpendicular and tangential forces that are actually acting onto the surfaces would be called as surface forces. Okay, we will define this. Body force is actually the force that acts on every particle of the fluid element. Just take an example of a weight. Weight is what actually, just think of mass is composed of several particles, and each and every particle of the body is being acted by the gravity. So each particle, the total weight of the body is composed of sum of the weight of each particle. So each particle is experiencing a force of, let's say, m1g plus m2g plus m3g, so on. So weight is actually thought of as a resultant force which is at the center of the body, so which is actually the sum of all the forces that are acting on every particle to which the mass is made up of. So as we know, we can define broadly classify force. There are two types of forces. One is the force which act at a distance. So it is something, a force which does not require a physical contact. For example, gravitational force. So Earth attracts every body towards its center without any physical contact. And just like the same as magnetic substances. So if you place a magnet and you bring some magnetic substance close to the magnet, so that magnetic substance, maybe iron nail, would be attracted by the magnet without any physical contact. So these are the examples of the body force which are actually called as force act at a distance. So without any physical contact, So this force is called the body force. And in deriving the Navier Stokes equation today, we will use only, we will ignore the field of electric field and magnetic field effects. So we will only consider the gravitational force that is acting onto the body. So as we know, the force per unit volume is rho times acceleration, and here acceleration is acceleration due to gravity represented by a vector g. So this is the only body force that is actually acting to a fluid element in our case today. There is another important type of force, we call it a surface force. So surface force is obviously different from the body force. Surface force is a contact force that actually acting directly onto the surface of the fluid element. So we call it a force at a contact, in contrast with the force at a distance. So body force is a force at a distance, whereas the surface force is a force act at a contact. So obviously there are forces which are being applied. It could be a pressure, or it could be stresses that are acting onto the surfaces. For example, in case of normal stresses, they are always perpendicular to the surface. Or it could be a pressure distribution over a certain body shape. For example, here there is an aerofoil, and here it is showing pressure distribution. So you see some higher pressure at the bottom, some low pressure at the top surface. So this results into a lift on an aerofoil. This difference of pressure results into a lift. So this is a typical pressure distribution onto that surface. So this would be called as a surface force, because pressure is acting directly onto the surface. It could be the force which is acting onto the surface parallel to the surface, or we call it a wall shear stress. So this is some sort of not a perpendicular force, but a tangential force. But also this force also act onto the surface, so it would be come into the category of the surface forces. Let's see if we have differential element. And our coordinate system is x, y, and z. So x is this direction, y is this direction, z is this direction. So the force which is acting perpendicular to this area, and the area is represented by the normal, and the normal is in the x direction. So we have a stress tensor. You already have studied in your solid mechanics course as well. So this is a tensor which is representing 9 components. So this quantity stress can be defined if we have a knowledge of these 9 components. For example, these stress tensors are called rank 2 tensors. And vectors are actually rank 1 tensors, and scalars are on rank 0 tensors, because only a magnitude is required to define a scalar quantity, so it is a 0 rank tensor. And 3 components are required in a vector to represent a quantity. It is called a rank 1 tensor. So if these 9 components are required to represent a quantity, it is called a tensor of rank 2. So stress is a tensor of rank 2. If you see here the subscript associated with the stress tensor, so the first subscript is actually defining the direction, and this to the right, and this I call it I and J. So here stress is in the direction of J, and where this stress is acting, this is acting onto this surface, and this surface is represented by a normal on that surface, and the normal is in the direction of X. So that's why this I subscript of the stress is representing the place where stress is acting. So this area is represented by the normal. So normal to this area is in x direction. That's why it has sigma xx. So if you look at this stress sigma xy, so it means the jth subscript is representing the direction. So the force is acting in the y direction. And where this force is acting, so this first subscript denotes the normal, and normal is in x direction. That's why you have sigma xy. Similarly for sigma xz, as you know, the direction of the force stress is in the z direction. So the jth component, jth subscript is denoting the direction, and the ith subscript is denoting where actually this force is acting. This is acting onto this area, and this area is represented by the normal onto this surface. So typically the diagonal component, diagonal element of this stress tensor are actually the perpendicular directions on this differential element, and all these off diagonal elements are actually acting parallel to the surfaces. So that would be responsible for the shear stress. So if we see this forces that are actually acting in the x direction only, so this is the component of the stress multiplied by the area. Stress has a unit of Newton per meter square, so multiplied by area, it would have a unit of force. So the force that is actually acting on this area would be sigma xx times this area, because this is dy, this is dz, so area is dy dz. Similarly, if it travels certain distance dx, its stress would be this normal stress plus some change in stress takes place as it moves in the x direction. So these are the two forces which are acting onto this side. Similarly, the forces can be represented by these expressions. If we look closely, sigma xx is here. So if you take the net force or net stress which is acting onto this fluid element is the difference. And this difference is, we cancel out this sigma xx and cancel out sigma xx. So what we end up with, the net force is actually not the stress but the gradient of the stress. So it is very important to understand that the net force is here on this fluid element is not the stress that is acting, but actually the gradient of the stress, which is how the sigma xx changes with respect to x is responsible, which is actually the net force which is acting onto the fluid element. And you see here the same differential element, and we have only, for simplicity, we have only included the forces that is acting in the x direction only. So the net force would be this force plus this force plus this force. So all these three forces which are acting in the x direction have been summed up together. So this would be the net force which is acting in the x direction. So here you see this volume is common, so obviously in the next step we will divide by the volume. This is the net force that is actually acting on this fluid element, and we divide by the volume, so we get this gradient of the stresses. So this is the force per unit volume, and we use a small f to represent the force per unit volume, and force per unit volume has a unit of Newton per meter cube. So this expression is actually denoting the force per unit volume in x direction. Similarly, we can write down the expression for the force per unit volume in y direction and force per unit volume in z direction. So you see these tau's are tau xx, tau y, tau zz are actually the diagonal elements, which are actually the normal forces, and the off diagonal elements are the tangential forces. If we see this stress tensor, so these diagonal elements represents the normal forces, whereas off diagonal elements represents the tangential forces. What I do here is I break this stress tensor into two parts. The first part is actually I have used P for hydrostatic pressure, and if you sum up together, you end up with the same stress tensor. Whereas this second term here is actually a viscous stress tensor, which has 9 components. So these are the normal components, and these off-diagonal elements are the forces or stresses which are acting parallel to the surface. So we can write in a shorter notation like this, because P here is an hydrostatic pressure, I here is an identity matrix of 3 by 3 order. So this term plus this term is actually the stress tensor, and we have a notation that stress is always outward, whereas pressure is always inward. That's why we have a negative sign here. So P here is a hydrostatic pressure which is always acting inward. Pressure always acts inward, whereas stress always acts outward. So this is a notation we have used. So we can write down the stresses in terms of the normal plus the viscous component. If we see here this viscous stress tensor, so when the fluid is at rest, what happens is the shear stresses are 0. We have already learned that the definition for the fluid which is in rest would be when the shear stress is 0. So if all these components are 0, so it means we can say the fluid is at rest. Only the pressure is acting onto the fluid element. So there are no shear stress tensor present. In contrast, if the fluid element is moving, so we see here when it is moving, so it has normal component as well as tangential component are responsible for because the fluid is something which cannot sustain the shear stress. So your stress tensor would be a combination of the normal and the tangential part. If we take the divergence of that stress tensor, so we have this stress tensor, and what we do is we take the divergence. So this is our del operator, which is a vector, and this vector is tensor of order rank 1, and if it is multiplied by the tensor of rank 2, so what you end up with? You end up with 3 components. That would be the x component, that would be the y component, that would be the z component. So if you see it closely, actually these the divergence of this stress tensor result into the components which are actually nothing, the net forces acting onto the fluid element, because these are the gradient of the forces or stresses rather, gradient of the stresses. So which is actually the net forces that is acting onto the fluid element. What we can do is we know that the net force per unit volume acting onto the fluid element can in the x direction can be represented like this. In the simpler notation, as we know, the stress tensor is the normal component and the tangential part. We can write the force per unit volume in x direction into 2 components, the pressure component and the shear stress component, which is acting tangentially. Similarly, we can write the force per unit volume in terms of for the y direction as well as for the z direction. So in x direction you have a pressure gradient in x direction, whereas in y direction you have a pressure gradient in y direction. So altogether you got in a simpler notation, in a compact notation, we can write the body forces that are acting, body forces per unit volume that are acting onto the fluid element is a combination of the pressure gradient and the divergence of this shear stress tensor. So we have surface forces which are actually acting onto the fluid element is a combination of the pressure gradient term and the viscous divergence term. And we know that body force is only here is a gravitational force. So according to our Newton's second law of motion, rho times acceleration is actually the force per unit volume, either the body force or the surface forces. So here what we can do is we can substitute the surface forces as well as the body forces in Newton's second law of motion. So what we end up with? We end up with this term is inertial term, because it is the material derivative of the velocity. So it's and density has a component of mass. Mass times velocity change is an acceleration. So it would be the force per unit volume, because it's the mass per unit volume. So this term we call it an inertial force per unit volume. So, and the body force here is rho times g, which is actually the gravitational force per unit volume. And then the surface forces. So the surface forces has two components: the pressure force per unit volume and the viscous force per unit volume. So this is what we have defined here is a momentum equation using Newton's second law of motion. So we have all considered the gravitational force, only body force that is acting. It means we are neglecting the electrical field and the magnetic field. And the surface forces are of two types: the normal forces and the tangential forces. So the inertial force per unit volume, depending on the magnitude of the gravitational force per unit volume, the pressure force per unit volume, and the viscous force per unit volume. So this is our momentum equation. What we can do is, this is in a vector form. So what I do now is to expand this into Cartesian coordinate system. So as you know, dV by dt is a material derivative. So since this is in a vector form and it is a momentum equation, so we have velocity has x component, and the velocity x component is represented by u. Similarly, the velocity has a y component represented by v, and the velocity in the z direction is represented by w. So actually this is not a one single equation, but it's actually a combination, three different equations for x momentum, y momentum, and z momentum. And this term is the local variation of the x component of the velocity, and this is the convective part. So u component, how the u component changes as you are moving with velocity u, v, and w. So this is the component of acceleration due to gravity in the x direction. So this is the pressure gradient in x, and these are the tangential stresses that has been acting onto the fluid element, if you are only considering the forces in x direction. Similarly, for the y direction and the z direction, we can write. So this is a vector form, and this is an expanded form using the Cartesian coordinate system, where x, y, z, and the velocity in x is u, velocity in y is v, and velocity in z is w. If we look at closely, how many unknowns we have in these three equations. As you know, the problem is space and time variables are involved, x, y, and z, and time. So these are our independent variables. So we have here x, y, z, and t. These four are our independent variables. But the variables in which we are interested in is u, v, w, pressure. So u, v, w, three components of velocity. P is the pressure, which is a scalar quantity, and 9 component of the viscous stress tensor. So altogether we have 13 unknown here. 4 are u, v, w, 3 component of velocity, p pressure. So 4 unknowns are u, v, p, and w, and there are 9 stresses. So altogether we have 13 unknowns. As far as the problem is concerned, we have 3 momentum equations, 1, 2, 3, and 1 continuity equation. So altogether we have 4 equations and 13 unknowns. Obviously, mathematically, the number of unknowns are higher than the number of equations, so the problem is indeterminate. So we cannot solve this problem. We have formulated using Newton's second law of motion, but the problem is mathematically indeterminate. Okay, now our attention would be focused on making it determinate. Okay, let's see what we can do. Okay, either we increase the number of equations or we reduce the number of unknowns. So, okay, first we do it as we know that the tau xy and tau yx, they are symmetric, they are identical in magnitude. Similarly, tau xz is same as tau zx. So instead of 9 components, now you have only 6 components. 6 plus 3 components of velocity and 1 pressure. So altogether you have 10 unknowns. By applying the symmetry principle, we have reduced the number of unknowns from 13 to 10. But the problem is still your number of equations are 4 and your problem is indeterminate. But we have so far 10 unknowns and 4 equations to solve this. What we do here is, Stokes actually has postulated a relation which is applicable for Newtonian fluids in 1845, long time back, which states that the shear stress would be proportional to the strain rates. In the first lecture, we have already seen that the stresses are actually Newton's law of viscosity related with velocity gradients. So what he has proposed that in here we have 2 types of stresses, the normal stresses and the tangential stresses. So for case of normal stresses, xx, yy and zz, we can relate using the velocity gradient by this equation. So this involves 2 types of coefficient. The first coefficient mu is actually called viscosity coefficient or first coefficient, and lambda is actually second coefficient. So if we replace tau xx with this thing in our momentum equation, so we can simplify, we will simplify later. Okay, let's see the shear stresses. Shear stresses would be, instead of 9, we have 3 components because they are symmetric. So these total 9 components reduces into 6 components. So each represented by 3 equations, these 3 equations and these 3 equations. And Stoke also has presented a relationship between the first viscosity coefficient and second viscosity coefficient, and he has done it experimentally. That's why we call it a constitutive relation. So momentum equation is a fundamental relation, whereas Stokes postulate or Stokes relation between the shear stress and the velocity gradients or the strain rates is a constitutive relation, or it depends upon a particular type of material by which it is made up of or constitutive of. So that is only valid for Newtonian fluids. So momentum equation is derived using the fundamental principle, that is the conservation of momentum, whereas Stoke has provided us an opportunity to substitute the tau xx part, tau xy part, tau yz part, xz part or yx part, and tau xx part into the momentum equation. So what we have done, we have stress tensor. So in our momentum equation, we have kept this inertial term, the gravitational term and the pressure term intact. And what we have done is, in the viscous term, using the Stokes relation, the 6 relations Stoke has postulated, we have substituted all these stresses, so that eventually you end up with, you get rid of the stresses and you end up with the velocity gradients. Same thing we can do it for y component and the z component of the velocity. So what we have done is simple. We have used these relations developed by the Stokes based on experiments, and this is simple. We have substituted in this expression of tau, and we end up with this set of equations. So, okay, we can further simplify. Let's say we will only talk about for x direction only, and similarly we will develop for y and z direction. So in x directions you have tau xx component, tau yx component, tau zx component. So these are the stress tensor terms in momentum equation. We take an assumption here for incompressible fluid. Incompressible fluid means the divergence of the velocity is zero. We have already seen in our continuity equation lecture, second lecture, that for constant density fluids, the divergence of velocity is zero. So this term, we get rid of this term. So we only left with this term in tau xx, and the rest remain the same. Now we can take a further assumption of constant viscosity. So here, as you see, 2 mu times w by w. So both terms, 2 is a constant, but mu and w by wx is changing with x. So if we assume constant viscosity, we can take out of that derivative. So here it takes out of derivative, then it would be w square u over w x squared. Similarly, this mu can be taken out of this, it would be w over w y square. And similarly, mu is taken out of that derivative in each term. Now we can simplify this by introducing our continuity equation. So our continuity equation is divergence of velocity is 0 or w by wx plus w v by wy plus w by wz equals to 0. So from this continuity equation, if we just substitute in place of w v over wx, substituted this thing. So what I have done is I have just brought instead of w v by wx, I substituted this thing, and then I have simplified. So at this point we see the last two terms are identical, so they can be cancelled out. So here we do it, these two terms cancels out, and we end up with this simplified expression. Since mu is constant, so what we can do is we can take further common, and we can write in this vector form this expression, which is an inertial term, which is a gravitational term, which is a pressure term, and which is a viscous term, which is a second order term of velocity. So this is a partial differential, second order partial differential. Similarly, we can write down the expression for y direction as well as for z direction, because this is the simplification we have done it. Similarly, we can do it for y direction and the z direction. So we can combine together these three components into a vector form as well. So instead of talking about x component of velocity, y component of velocity, z component of velocity, we can write in terms of a velocity vector v, which has three components, u, v and w. So this would be your rho times acceleration, inertial force per unit volume. This would be the body force, that is the gravitational force per unit volume. This is the pressure force per unit volume, and this would be the viscous force per unit volume. So here, if you look at this problem, we have four unknowns: u, v, w and pressure. Because we have got rid of the stress terms by thanks to Stokes postulate, that we get rid of those stress terms and we only end up with the velocity terms. So now the problem is determinate, because we have four unknowns and we have four set of equations. 3 is momentum equation, 1 continuity equation. So in this way we will be able to solve our momentum equation, and this final form is actually called the Navier Stokes equation. So once we have used the Stokes hypothesis, a constitutive relation of Stokes is applied into momentum equation, and simplification process, we end up with an equation, what we call it a Navier Stokes equation. So Navier Stokes equation is a combination of a fundamental equation, which is actually a momentum equation, plus the constitutive relation of Stokes. So, and obviously we have used in our derivation the continuity equation. So using all these equations result into an equation that is actually called Navier Stokes equations. And in the later part of the course we will explore each of the term, and we already have seen that the problem here is determinate.